Hello everyone, welcome. Today this is Project 3 Defects in Diffusion with silver, palladium, and indium nitride, presented by Ryan, Laurent, and Dustin. And this is me, Laurent Kingue, presenting this project. Okay, the first slide, as stated, is vacancy defects in silver. Let's go over the key terms. QV stands for vacancy defect, the energy required to create a vacancy or a missing atom in silver, which is given to us here is 1.1 eV. T is temperature, obviously. Here it is 20 Celsius, or converted to Kelvin it is 293. The Boltzmann constant, the fundamental constant, here it is 8.62 times 10 to the negative 5 power times eV per K. And our Avogadro's number, Na, will always be 6.02 times 10 to the 23rd atoms per mole. Molar mass of our unit is 1 silver, which is 107.87 grams over moles. And the density of silver is 10.49. To find the first, we need the total number of atoms per cubic meter. That is right here. And TOT is phi at times Na over m. Phi being 10.49 times 10 to the third power. M, our molar mass, which we have right here, and Na, which we have right here. And the number of vacancy defects, and V is the formula right here. And we have, which we need the TOT, which is what we solve for over here. And if you put that all together, you get this formula right here. 5.686 times 10 to the 28 times all of this, which will land you this number right here. Now we're on to the next one, vacancy defects in palladium. It is the same formula, but some things might be slightly different. The QV, the vacancy defect of silver was 1.1, and this one it is 1.5. Same temperature, and obviously Boltzmann constant stays the same, is a constant, and Avogadro's numbers also stay the same. Our molar mass is a little different. It is no longer 107.87, it is 106.42. And these are other things that might be altered from silver. That is not the same with palladium. And of course, like we said in silver, these are different formulas. So, no, same formulas, just different values for each formula. And it's the same thing for the total number of vacancy defects, which is right here. Instead of 7.13 times 10 to the 9th, we get 1.09 times 10 to the 3rd for vacancy defects. And instead of 5.86 times 10 to the 28, we have 6.78 times 10 to the 28 for our cubic meter. Now we have Schottky's defects in indium nitride. Now, Schottky defect, so is QV, is energy required to creates a Schottky defect, which is a type of vacancy where atoms leave their regular position in a crystal. This is the formula for that here, which if we do for indium nitride, will come out for 4.75 eV, of course T temperature, and our Boltzmann constant is now 8.62 times 10 to the fifth, negative fifth, eV over K. And of course here we have our Avogadro constant and our molar mass of indium. And of course here the total number of atoms per cubic meter, which is Vp over m divided by Na. That will come out to this. And here is the number of Schottky defects. Now notice that there's a factor of 2 in the denominator because Schottky defects involve both cation and anion vacancies. So you substitute the equation and you will end up with this, which will lead you to 4.61 times 10 to the negative 13 power. Now in this slide, we're talking about Frenkel defects in indium nitride. Frenkel defect is a type of defect where an atom leaves in In this slide, we're talking about the Frenkel defects in indium nitride. Frenkel defect is a type of defect where an atom leaves its regular lattice position and occupies an interstitial site, which is a space between atoms and a crystal structure. And we still here have our energy for vacant creation, which is right here, our temperature, which is right here, and our Boltzmann constant, which is right here. Of course, Avogadro molar mass. Now the total number of atoms per cubic meter at DOT, same formula, different values just have to be plugged in. Now for our interstitial state, which for indium nitride has a hexagonal closed packed structure. In an HCP, there are 6 atoms, and there are both tetrahedral and octahedral interstitial sites, which is right here, 12 tetrahedral, 6 octahedral. So if you add these two and divide by 6 atoms, you will get 3 atoms for an interstitial atom. And then here is NF number of Frenkel defects. NF is TOT, which is cell 4, and NI being 9.54 times 10 to the 28 right here. When you solve for all of that, you should come out to 7.99 times 10 to the negative 13 defects from here. Now in this slide, we are doing diffusion of silicon. The D in this equation represents the diffusion constant. That represents the diffusion of how fast atoms or molecules spread out, with D0 representing the pre-exponential factor, which represents the diffusion coefficient at an infinitely high temperature. QV being the activation energy required for diffusion. KB, Boltzmann's constant, which we know already, is 8.62 times 10 to the negative 5 power of EV over K, and T being temperature. Now, once we sub in everything, 1.5 times 10 to the 5th, and you plug the rest in. D1 and D2. The only difference is, as you see, the temperature of D1 is 300, the temperature of D2 is 600. Which will lead you to these two answers. D1, which has 300 Kelvin, is 2.02 times 10 to the negative 22, and D2, which has 600 Kelvin, is 5.51 times 10 to the negative 1 power, 10 to the negative 9 power, excuse me. And now this equation is diffusion length, where L represents the diffusion length, which tells us how far particles can diffuse over a given time. L is obviously length, and T is diffusion time. D obviously being what we have over here, which is the diffusion coefficient. We plug that in, and in here we're using 60 seconds. You get 1.1 times 10 to the negative 10 power. For D1, which correlates with L1, and for D2, which correlates to L2, is 0.005, all in M. And our final slide is the diffusion length of carbon. Last slide we did diffusion of silicon, this one is carbon. Obviously, we're using the same formula, diffusion. We know what QV is, KV, and we know T. Instead of using what we used last time, we'll replace it with 1.329, and with 10 to the negative 10, and 1.329 times 10 to the 5th. Obviously, we're still doing the difference in temperature, which is 300 and 600. The thing that changes is the outcome of these. And when you plug all that in, D1 is equal to 4.47 times 10 to the negative 29, and D2 is equal to 7.71 times 10 to the negative 20, which will later correspond with our diffusion length, L. We know D stands for diffusion, and T stands for time, 60 seconds. And L1 again correlates with D1, so we plug in D1 with L1. 60 seconds, you get 5.18 times 10 to the negative 14 power. And L2, you get plug in D2, 60 seconds, you get 2 and 15 times 10 to the negative 9 power. That's all my group has for you guys today. Hopefully you enjoyed this video, and I hope you learned something. Please have a good rest of your day.